really well fourth hour, and when that happens, it never goes well the rest of the day. So just the worst feeling when I have a good class fourth hour. All right. So I scan on this thing, and yeah, you'd call that 1050. Okay. So over here, if I draw a free body diagram for Harding, H, I'm going to have 1050 newtons down. That's FG, Harding, comma, Earth. Okay. And I'm going to have 1050 newtons up. That's going to be F smoosh poosh, Harding, comma, scale. And then my first question to you is this an appropriate thing to do here? Because these sizes these forces are same size, opposite direction. So over on the pair deck, is that the right thing should I be including fun shapes here? Oh my gosh. Let's see what we have here. No, because the feeler dealer labels aren't opposite. No, different feeler dealers. Nope. No, they're not force pairs because one is smoosh poosh between Harding and the scale. The other is gravity between Harding and the earth. Okay. They are equal, but they are not pairs of the same force. So that's solid. Okay. It's good to see. You're not falling for it. Yes, they are the same size. Yes, they are different directions, but they are not a force pair because they are different interactions. They just happen to be the same size in different directions because the forces on me are balanced, and those are the two forces. Okay. Well done. I think you're ready to play. So I'm going to hop on this scale. Hopefully I get a reading. And what I'm going to do is jump. Yeah? How about that? Gee, Mr. Harding, you're very athletic. Okay? So I'll grab a screen cap of this. I don't know why this thing is playing so rough today. Come on. Click on you. Click on you. Click on you. There we go. I'm going to grab a screen cap of this graph. Oh, for the love of Pete. Hide that. Sorry, I'm just trying to make sure I get the time axis on this as well. Ooh, really? There we go. I've got to figure out what the magic is here, but for whatever reason, this is acting weird with tabs today. All right, so I got the graph. I come over here and drop it right there. And my next question to you is going to deal with the graph. Oh, Atlanta. What? There we go. So that's point A. How about use a different color than the graph is starting? All right. So this is A. That's B. Let's call this C, D, E, and F. And my question to you is, what is the interval where I'm in the air here? Okay, so yeah, do this. Oh, for crying out loud. There we go. So what to what? What's the interval that I'm in the air? All right, this is running smoother than last hour. That's a good sign. So out there in the world, you could give them this or you could give them that. So check this out. I got C to D, I got B to D. Okay, C to D or B to D. So take a gander at that again and chat with your neighbor. When am I in the air?
And then there's also that amount of time where it's happening. Oh, wait, did he say B and D? Yeah. Oh, I don't know if one's right, but B and D makes sense.
Oh, well,
I mean, you could have just
it's
straight line.
because of the difference in force.
All right. So let's go back over here and look at this. Unfreeze. So B to D, C to D, B to D, C to D, B to D, C and D, C to D, C to D, C to D, B to D, C to D, C and D. C to D because it's the interval in which your body isn't exerting any force on the scale. C to D, scale says 0 because since you aren't touching it, it can't read you. Okay? So how about ponder that and then go back to your response. When am I in the air? AKA not touching the scale. All right, so I was just checking this out for myself because there are a couple people wondering about how sensitive the scale is. So here's 4.44 seconds. And then there's a couple of readings here, 4.42, 4.40, 4.36, 4.34 is when we're at the peak. So there's what, 1, 2, 3, 4. Basically 5 readings between the peak and when the scale goes to 0, okay? Reading every 200ths of a second. So there's not a huge difference between C to D and B to D, but there was only one person that had B to D initially, and now a lot of you are writing it. I was just kind of throwing that up there so we had some contrast. You're easily swayed. I'm sticking with that. The reasoning that was offered up there, C to D, the scale reading is 0. There's no interaction with it. So that's safely the margin that I'm in the air, okay? So I guess what I'm looking for now is, can you consider what does the free body diagram look like on me from C to D, okay? So if you were to draw the free body diagram for me from C to D, what would that look like? Let's see here. That's going to happen here. Free body diagram from C to D. Harding. Alrighty. There we go. So I'm gonna lock it for a second just so I can show you this. So here's what I'm seeing. Okay, that's kind of the contrast. So run that by your neighbor. Which of those is most like what you have? Okay, and why?
I tend to balance with it. I have the boards are not floating in the air, moving constantly.
And then please don't include your FU in your free body diagram, especially if I've said that to you many times.
It's real test too.
All right, so now we're looking homogeneous. It's that. Oh, dang it. That's not homogeneous. Who did that? All right. Why are almost all of us not including an upward arrow after I leave the ground? Ronan? No longer interacting with anything that's going to lead to a force in the upward direction. Okay? So once I leave the ground, if you did a system schema for me, it's just a line connecting me to the earth. That's the gravitational interaction. Okay? So my free body diagram ends up being this FG Harding, Earth, 1050 newtons. Balanced or unbalanced? How unbalanced are they? 1050 newtons. So I'm going to draw an FU right next to this thing that shows that this is unbalanced by 1050 newtons downwards. Okay? So there's my FU. If my FU is 1050 newtons, poopy. There we go. Sorry, so FU right there. We need to have like a little thing you whistle when I forget to unfreeze the screen, so then I'll just like, I'll know right away. So there's the FU, 1050 newtons. Hey, I know those people. 1050 newtons. If I do FU divided by mass, I'll get acceleration. So I've got 1050 newtons. What's my mass? Any of you work at the state fair? Guess my mass. FG is 1050 newtons. Yeah, something like that. So 105 kilograms here, okay? So who's got a calculator? 1050 newtons divided by 105 kilograms. About 10, okay? Right? That's where that 10 comes from. 10 newtons per kilogram or 10 meters per second squared. Now, something to be aware of is this FU is pointing down. So this acceleration is negative 10 meters per second squared, okay? The direction of that acceleration. All right. Let's go back down and take a peek at the graph again. So that was a free body diagram from C to D. That's after I've left the ground, though. Let's have a little think about before I leave the ground. What does it look like if you draw a free body diagram? Sorry, I got to pop over here quick. A free body diagram at B. Okay, free body diagram at B, and you can kind of use the graph there to read stuff. So here's Harding at B. Go ahead and draw that. And again, if I just said nice things about you in an email to home, it'd be super cool if you participated. So Wait, would he have said nice things about me? So at B, what would you draw for the free body diagram? Okay. So I think it would be helpful to consider how we're modeling me, okay? And I would encourage you to model me as a ball of mass at my belly button, okay? Typically, that's how we want to deal with like objects like humans. So imagine just a sphere of mass right here. A is when I'm at the lowest point in my crouch. Like if you look on that graph, it kind of goes down a little bit. So I was crouching down, okay? So the ball of mass is here. This is A, and then C, right, is when I've left the platform. So I think there's some issue as to what models apply here right now. Okay, so think about this ball of mass at my belly button, A to C. What models apply there? Okay, and see if that helps you think about the number of forces and what should be happening there. And again, I can make this graph bigger. Like, go ahead and use the graph to try to make this thing quantitative as best you can. So here's a little bit of what I'm seeing right now. There's some disagreement as to numbers of arrows, okay, in terms of what's happening here. So let me throw this question to you. For this free body diagram at B, come on, man. Okay, should that be 2 or 3 arrows? And should that be BFPM or UBFPM? All right, I'm gonna lock it for a sec because I have some variations here for you to look at. So I've got a couple of 2 arrow answers and a couple of 3 arrow answers. So 2, UBFPM because of upwards acceleration. 3 arrows, UBFPM, the force you have to use to jump makes an unbalanced force. UBFPM 3 because your mass hasn't changed, the scale's still pushing up, and you are putting force on the scale. 2 arrows, still only Earth interacting with Harding and scale, UBFPM. Harding is accelerating as he jumps upwards. So it must be unbalanced. Okay, so can you ponder these with your neighbor for a moment? I'll unlock it and you can do as you need, but there we go. All right.
But there's no other speed. Not for speed, yeah, it has to be larger. Yeah, there's nothing else is really
What up?
Like, are we doing this as content from the last test or for the course?
I'm doing good. All right. Go back to your free body diagram. Make any revisions you feel are necessary after that conversation. Again, in terms of model, it seemed pretty universal. People were saying UBFPM. Is your diagram agreeing with that at present? Again, think about what's happening to that center of mass here from the point I'm in this crouch to the point that I leave contact with the platform. So here I've got 2,000 up and down. I've got 2,000 up, 1050 down. Okay. So consider those two things in your group. Should be 2,000 up, 1050 down, 2,000 up, 2,000 down. Run that by your neighbor real quick. All right, let me hold you there for a second because this is what I was hoping for my birthday. I need you to ponder this one with your neighbors. What are your thoughts on that?
Because that one implies on a scale, which is a commercial.
Oh, okay.
And then contrast that with somebody who's saying this.
I mean, like, why?
Right. All right, so I'll unlock it. Back to your free body diagram. Go ahead and make any revisions you feel are necessary there.
Because he doesn't change. Scale. Scale's not.
Okay, or perhaps this. You think about that in contrast to that. And I can't get them. I wish I could display them side by side, large, but I can't. So it's either, the difference is 2,000 up or 1050 up. The belly button, my friends. The belly button. Okay. So think about what the belly button is doing during this interval. And maybe we do this. All right. So of these three options here, I'm going to give you a third. Which one is correctly explaining the motion of the belly button? Got that? And this would be unbalanced up. This would be, where's the one? This I think was balanced down. And this is unbalanced, or I'm balanced down. That makes no sense. Sorry. Unbalanced up, balanced, unbalanced down. Okay, so run that by your neighbor. See where you land here. Oh crap! What I forget to hand out earlier from Octavius. Ruh-roh.
Oh wait, that's already. Oh wait, you're
All right. So maybe we just go with this approach. Here's what everybody's looks like all at once. Oh, wait, that's not helpful. That's not clear. There you go. Generally speaking, it looks like a majority would say 2,000 up and 1050 down. That would result in an FU up. That would mean the belly button is accelerating up. Okay? So let's run with that for a moment. This FG is unchanged because my mass is unchanged. Harding, comma, Earth. This is 1050 newtons. That's all the higher up that goes. Okay. 2,000 newtons up. This is F, smoosh poosh, Harding, comma, scale. Because that's what this reading is here. This is reading the scale. The scale says that the interaction Harding, comma, scale, or scale, comma, Harding is 2,000 newtons there. Okay. So, le boop, something like that. All right. That took a little more thinking than I wanted here. So forces are unbalanced. They're unbalanced by about 1,000 newtons there. Okay. So we figure out an acceleration reasonably. But in looking at that force graph, what would be an issue with saying that that's the acceleration I experience while jumping up? Like, what do you notice from A to C? Can you run that by your neighbor really quick? What would be an issue with me using the unbalanced force at B and saying that that's my acceleration while I'm pushing off from the thing? Okay. And so this is why I'm tying it into old models and new models. In the old model, we kind of dealt with like a constant amount of force, but here the force is varying in time. And so in order to get information about the motion here, we got to do something that takes into account that the force is varying in time, okay? And this is a graph of force in time. The units here are Newton seconds. I can get impulse here from this, okay? I can get impulse from this thing. If we look on the graph over here, time A corresponds to right about 4 seconds, and C corresponds to, that's about 4.44 seconds, okay? So I can label that on the graph, TA, 4.0 seconds, TC, 4.44 seconds. So then if you look at this, you've got this triangle here, and this rectangle underneath it. And what I'd like you to do is use the information that you have from the graph here to try to approximate my change in momentum, okay? So go for that on your own, and I'm going to throw you onto a number slide over here. Number something. So what's my change in momentum? Don't talk to other people. Just do math. Where'd that go? So again, you're finding my change in momentum from this. All right. Let me shut that down for a sec. Just take a peek at it. So we've got a couple different clusters here, but a lot of the dots are at about 671. Okay. If you go in here and look at the shapes, thank you. Just like whistle, do you want to build a snowman or something? And then I'll just. Right? No? Okay. Fair enough. So you got this rectangle, and that's going to be roughly 1,000 newtons times 0.44 seconds. And then you got that triangle on top of it, which is going to be half of 1,000 newtons because it's from 1,000 up to 2,000 times 0.44 seconds. So 440 plus 220, ballpark 660 Newton seconds. Okay, that equals the change in momentum, which is equal to my mass times my change in velocity. So if you take that 660 Newton seconds and divide it by my mass, which we said was about 105 kilograms, you'll get my change in velocity. So go ahead and slap that out quick, right? Something in the ballpark of 6. .3. Okay, so that's the change in velocity that I experience as a result of pushing off the platform. What I'd like you to do semi-quickly is go ahead and draw the velocity versus time graph from that point, so that's C, yeah, until I reach the highest point in my jump, okay? So what does the velocity versus time graph look like from C until my max height? Velocity versus time graph. And you only need to concern yourself with the velocity versus time graph from that point C when I leave the platform until I reach my max height. Let me just show you this really quick. This is what I'm looking at right now for graph shapes. Okay, so ponder that with your neighbor and then revisit your graph real quick. From the point I leave until I reach my maximum height. Friends, think about my velocity at my maximum height. Okay, when I'm at the peak of my jump, how fast am I going? Some of you are drawing position graphs, more than a couple of you. Or maybe I should say this. Hey, we talked about the free body diagram for after I leave contact with the ground. That's this, okay? So you know what my acceleration is here, okay? This is my free body diagram after I leave contact with the plate. That should tell you something about the shape of the velocity versus time graph. Again, C is where my feet leave contact with the platform. All right, so now it's looking like this. You got the general idea. My velocity starts at 6.5-ish. I don't want that. My velocity is like 6.5, and it's going to go to 0. I've got a constant acceleration, so that should be a straight diagonal line or as close to it as it gets. The slope of this is negative 10 meters per second squared. Okay, and acceleration equals change in velocity times change in time. So negative 10 meters per second squared equals 0 minus 6.5 meters per second divided by t. So therefore, t is equal to negative 6.5 meters per second divided by negative 10 meters per second squared. That means the time for this is 0.65 seconds. Now I can calculate the area here. I can figure out how high up I jumped. Oh, come on. Do it real quick. Do it. Do it. You can do math. Half of 0.65 seconds times 6.5 meters. What do you get for that? Half of 0.65 would be about a third. A third of 6 is about 2. Yeah? You jump at about 2 meters. Watch. To the 2 meters. See? Put it 2 meters there. Crap, what's up with that? We'll fix it tomorrow. All right. Learning a little something about impulse.